Okay, in this video we're going to talk about a strategy that we're going to use for problem solving in kinematics. And I want you to understand that this strategy was developed in conjunction with students that I've had prior, and that it was an open dialogue between them and I, where we would openly discuss what was working and what wasn't working to help eliminate some of the mystery of problem solving, especially in kinematics. And one of the biggest problems that students generally have is which equation should I even start with? Because whenever I do stuff on the board, it looks like that's the way it should be done, and it's so clear and concise and straightforward. And students don't understand how to get to that point. So they're always asking, well, how did you know to use that equation? I just want you to understand that this is not a strategy that you should just shrug off and try to go it alone. It is exactly the way it is for exact reasons, and some of those reasons we'll discuss as we go along. So, in order to solve problems in kinematics, there are two things that you need to know. The first is that the equations of motion are only valid for portions of motion where the acceleration is constant. That means it does not change in size or direction. What this is going to mean for you is that in some problems, you might have to break the problem into parts. So, for example, if you're doing a problem where a driver is at a red light, and so the light turns green, they step on the gas and they accelerate uniformly until they reach 20 meters per second, then they drive with a constant velocity. How far did they drive? That is an example of what we would call two-part motion. And you would have to break the motion where the acceleration changes. So on a graph of velocity versus time, we would see something like this. There would be an increasing velocity until you reach your maximum speed, and then a constant velocity. And it's at this point right here that you break your motion. So this is part one, and this is part two. The other thing that you really need to understand about the equations of motion is that you can only use the equation on one object at a time and also one part at a time. So what that means is this. You cannot use the equation of motion twice in part one. For example, the velocity function. You could not use the velocity function twice for part one. However, you could use the velocity function once in part one, and then you could use it again for part two, because those are considered to be two separate motions for the purpose of problem solving. The other thing is you can only use the equation of motion on one object at a time. And in the difficult example that I'm going to do for you, we're going to see that we have two objects where one object is accelerating to the right and the other object is accelerating to the left. I can use the position function for each one of these objects because this object has its own displacement, which is separate and distinct from the second object. So just remember that rule. One object at a time, one part at a time. So you may use the same equation more than once as long as you follow the rules for using the equation. There are 4 basic steps that you're going to follow when problem solving. And the first step is to sketch a spatial diagram of the situation and label the information at the various locations. This is going to be absolutely necessary in two-part problems or two object problems. The second thing you want to do is you want to identify each object and the corresponding information that goes with each object. And you want to write it down neatly and as organized as you can, and you should be using the model that I set up below. So here's your basic organizational strategy. You're going to have object 1, and this could be for part 1, especially if you have multi-part problems. Object 1, part 1. You always want to take note of what is X initial, X final, V initial, V final, A, and T. These are all things that you want to write down for the first object. And don't forget that X final and X initial come together to form the displacement. And oftentimes that's the only piece of information you're going to need, because the initial position is going to be established by you. You're just going to set the origin of your problem at the starting point of the object. Then if you have a second object or a second part, you're going to do all this stuff again. So you'll have X initial 2, X final 2, V initial 2, V final 2, A2, and T2. And these two terms come together to form D2. You want to make sure that you make generous use of subscripts. Okay, so for example, in object 1, part 1, I failed to label these as 1s. But they should be. And that should be D1. And I've labeled all of these as 2s, although V initial doesn't look like it has a subscript. So let's fix that. There, now V initial has a subscript. And the thing is, you want to make sure that you don't forget about hidden information or implied information. And implied information could be things like the direction of acceleration. It could be V initial. Did it start from rest or did it come to rest? And this is particularly important when we get into free fall, because we have a couple of assumptions that we make for free fall. Now, in step 3, you are tasked with picking a primary equation. The primary equation is extremely important because this is the one that's going to keep your problem solving grounded. It's going to keep you on a level playing field. It's going to keep you from getting lost and confused. This is the step that's not really emphasized in your textbook. There is no right or wrong equation to use as your primary equation, other than to say that the primary equation should have whatever it is you're looking for. Now, what I mean by that is this. If you're looking for the final velocity, right? Maybe this is what you're looking for. You would not use this equation. Doesn't make any sense to use that equation. There's no v final in that equation, right? So make sure that whatever equation that you're going to use, make sure that it has what it is that you're looking for in it. Now, the primary equation is going to be based on the information that you have and instinct, all right? And you're going to do this for each object in each part. In theory, it doesn't matter what your starting equation is. The only thing that's affected by the starting equation is the efficiency with which the problem gets solved. The only thing that is affected by your starting equation is the efficiency or the number of steps that it takes in order to actually solve your problem. Now, once you've selected your equation, the last thing you're going to do is you're going to solve that equation for what you want. And once you've done that, you're going to go through your checklist. And what checklist am I referring to? Well, if we use the position function as an example, d is equal to v initial t plus 1/2 at squared. And let's say I'm just solving it for displacement. Then when I say go through your checklist, what you're going to do is you're going to ask yourself, do I know v initial? If I do, great, check it off. Do I know time? No, I don't know what the time is. Do I know the acceleration? Nope, don't know what that one is either. And here, time, I know it. And so if there's a quantity that I don't know, then I'm going to have to look for that value somewhere else. Where do I come up with time? Well, maybe time would come from this equation, v final equals v initial plus at. And so solving that for time, we get v final minus v initial divided by a. And the acceleration, maybe that's going to come from v final squared equals v initial squared plus 2ad. And so we get v final squared minus v initial squared over 2d is equal to a. And so now we can substitute those values back in. We get d is equal to v initial times v final minus v initial over a plus 1/2 times v final squared minus v initial squared over 2d times t squared. But here, if we go through our checklist, v initial we have, v final we have, right? T, we got to convert this one, still using v final minus v initial over a, so we still got work to do there. And we've reintroduced acceleration here, and so we would just substitute that in. I'm not going to take this any further, but that's the idea behind this strategy. And that if something goes wrong, it's as simple as going back, following my arrows through. Because one of the biggest problems I see with my students at kinematics is that they don't find something to ground the problem, this first equation. And so what they do is they just use all the equations and they calculate all these various quantities, but they don't know how to put them together in a meaningful way. And so that's what this strategy is all about. It's about making sure that you don't go through rambling calculations. All right, now, this particular demonstration here was, really busy, a lot going on. There's a lot of substitutions that we have to make, which tells us that we probably have a more efficient way of solving that problem. But we're getting away from the important thing here, and that is, what are these steps that we go through? So getting back to step 4, we want to solve the equation for what you want, and then you want to go through your checklist to verify those things that you need to find elsewhere. So we're going to go through the checklist. And any information, we got to find it somewhere else. Okay, where can you find that elsewhere? What is that, those other places? Well, you can use other equations like I did over here in this example. It might be that you're looking at part 2. There could be a relationship between object 1 and object 2 that you just haven't identified yet. So there's lots of places to come up with missing information. And sometimes you just picked a poor starting equation in the first place. Step 3 maybe needs to be repeated. And I'm going to go through some examples where I use all four, or I should say all three equations of motion, so that you could see that it doesn't matter what the starting point is, but the amount of work it takes to get through to the end, that does matter. Okay, so the last thing that I want to mention here, actually a couple things, but one, let the problem guide you. That's huge. You shouldn't have to reason your way through everything. You don't have to be able to see what the end is from the beginning. You don't have to know in your mind's eye what each individual step is going to be. You take each step one at a time, solving whatever the little problem is that you come across with each individual step. So you want to let the problem guide you. That's a tough one to learn, but once you get it, you'll be glad that you did learn it. Now, this is huge, and I don't know how to say it any other way than this, but there is no substitution for intuition, which can only be earned through experience. And lastly, don't ever forget, some solutions are just easier than others. Okay, so in the next video, I'm going to go through all four of these steps solving a problem, and I'm also going to do it using multiple equations as starting points.